Okay, looks like we're recording. It seems to be working today. Fingers crossed that it actually takes. We will see. Okay, so picking up where we left off last time, we were talking about spherical coordinates. We're almost done. The remaining things to be said are pretty quick. So you'll notice, for example, this process of converting a rectangular equation to a spherical equation is a lot like an analogous example from polar coordinates. Namely, pretty much what you're going to be doing is plugging in your existing formulas for converting between these two coordinate systems. So we already, for example, we know x is rho sine phi cosine theta. That's one of the formulas. Otherwise known as x equals r cosine theta. Again, that's how you remember it. But you can also save yourself some trouble by expanding out a square before you start plugging in, because if you expand it out, and then you might be able to notice, for example, oh, look at this is rho squared, and now you just saved yourself some trig, dealing with trig identities and et cetera. So time saver, error avoider, right? Nice trick. Okay, all right. So let's see, moving along. This business about standard basis vectors, of course, you know the standard basis vectors in rectangular coordinates, and there's different ways you can think about these. One way to think about these vectors is that they are unit vectors, each of which points in a direction where only one coordinate is increasing, right? So, for example, this vector, that's pointing in a direction where only x is increasing. In that direction, y and z are at least momentarily constant. Okay, so you can talk about how to do the same kind of thing in different coordinate systems. So, for example, if you're at this point right here, you could ask, which direction from that point would I move so that only r increases? Well, if you move that way, then r is increasing and theta is not. Theta is constant. Right? And a little bit of algebra can persuade you, or a little bit of geometry, I'll say, can persuade you that this is the formula for that unit vector, keeping in mind, of course, that this position vector, xy, is parallel, and so just divide that position vector by its own magnitude. Okay. All right, now, next question. How would you figure out what the e theta vector is, the direction where only theta is increasing, at least momentarily? Different argument to be made here. I prefer, this is just my own personal preference, to think of this as just a 90-degree counterclockwise rotation of the ER vector. And if you rotate that, then there you go. There's your formula for E theta. So real quick side note. So I know that this business about rotation is something that is prerequisite. So that's linear algebra, right? And I want to remind you of the broad strokes of how to make this argument. Broad strokes. And I want to make sure y'all can fill in the details. Recall that that rotations are linear transformations. Linear transformations are represented by matrices. Matrices are understood by the columns. And the columns are the images of the standard basis vectors. So if you want to understand a rotation, for example, a 90 degrees counterclockwise rotation like that, just ask, what does that rotation do to standard basis vectors? You can infer from that the columns of the matrix, and then multiplying by that matrix will do this. So make sure you can fill in those details. That is important. It is going to come up significantly in this class. It's just one of the really useful geometric facts about linear algebra that, again, it's going to come up a lot. Okay, if you're not clear on any of that linear algebra stuff, come to my office hours. I'll be very happy to talk you through it. We'll flesh out all the details and make sure that you're good with all that stuff. Okay, that's polar coordinates. Cylindrical coordinates, yeah, it's pretty much the same as polar. Put a comma 0 at the end, right? And then there is, of course, the third standard basis vector, which, of course, is pointing straight up, which, of course, is just E3. That's an easy one. Okay, spherical coordinates. Another couple of, familiar things, I'll say. We'll start off with E theta. The E theta in spherical is exactly the same as the E theta in cylindrical, which is morally the same as the E theta from polar, right? So that one's almost a recopy. The E rho you'll notice again is just position vector divided by its own magnitude. So there you go. Position vector xyz divided by its own magnitude. This time being rho, of course. And then the tricky one. The tricky one is how to come up with E phi. And the really slick move there is to realize that it is just from the picture, it is perpendicular to both of the others. And we know the others. And we know that those others are unit vectors that are perpendicular, and therefore the parallelogram has area 1, and so in fact this cross product is the desired unit vector. So real slick little observation there. Different ways you can do it, of course. Okay, all right, so good to know what these are. We're not going to actually use them much in this course, but outside of Math 219 and some other contexts, there are certainly some situations where one could use them, and therefore in your futures, very likely they may be used, and you may see them. This is what they are and what they mean. Do be sure to note certain bad news items about them. They're not constants, like the rectangular standard basis vectors are constants. Right, ones and zeros, they don't ever change. They're always the same. And they don't play nice with linear combinations, right? So in rectangular coordinates are coefficients in a linear combination. This is arguably one of the features that makes standard basis vectors so nice in rectangular coordinates. But the, kind of analogous, you would kind of hope that maybe something analogous would be true in spherical coordinates, but alas, it is not. It just doesn't work. So these standard basis vectors, they have a role, but they're not anywhere near as nice as rectangular standard basis vectors. Okay. All right. So let's see here. That is the end of Chapter 1. We are now moving on to Chapter 2. There's a bunch of kind of lingo and terminology and definitions that have to get said here at the beginning. I am going to go kind of quick through this stuff because it is all pretty readable, I think. But certain key things I think really do need to be said. First of all, what is a function? A lot of students misunderstand what a function is and think a function is a formula. And in a lot of contexts, you can kind of get away with that. But we're going to have to worry about things a little bit more carefully, and certainly in future contexts, you'll need to be more careful about it. So I want to remind you, or let you know, whichever is the case, that really a function is three things. It's the trio of all three of these things. So specifically, a function it's a domain, which is where the inputs come from, combined with a target, which is where the outputs go to, combined with the rule of assignment. But very often this is a formula that tells you how to compute the output for any given input. So, again, if you have a formula that describes a function, then that's just one part of it. That's the rule of assignment. But the function itself, the function is the trio of all three of these things. Okay, so quick examples. If you look at the natural log function, and this is a function, and notice it's defined for any positive real number. Right? Natural log defined for any positive real number. And the result is always a real number. So domain is the positive reals. The target is all reals. And the rule of assignment, I'm going to just say, natural log. I mean, it's the formula for that is written down elsewhere, and we don't want to worry about that. It's a pre-existing defined thing, so I'm going to call that the formula. So again, three things. Notice also the notation here. This is a very common notation I'm going to use a lot, where the function has a name. We write the name first, colon, which means, okay, now, pause, let me tell you a couple things about this function. And then domain, arrow representing the action of the function, taking things out of the domain and putting them into then the target. Okay. All right, so very common notation. Here's another example. This one seems a little bit silly, but this does allow me to fairly conveniently show you examples of related but different functions. So I've got three functions here, f, g, and h. All three of these functions are different functions. But all three of these functions have the same rule of assignment, namely, for any given student, the value of the function is that student's ID number. Now notice, that's not a formula. There's no algebra in the definition of this function, right? This is a rule. You give me any student, there is exactly one student ID number for that student. All right, so what is it that makes these functions different? Well, if you take these two functions here, f and g, the difference is that they have different targets. That seems a little silly or pointless or irrelevant, perhaps, but we're going to see in about a page or so that this actually really does matter. Here, I'm saying, look, the ID number, by the way, that's going to be an integer. Down here, for this different function, I'm going to say the ID number, well, it's going to be a real number. Now, these are both true statements. Every student at Duke has an ID number that's an integer, and it is also, of course, a real number. So both are fine, but they are different targets, and so that makes these different functions. Again, it's a subtle, perhaps, right? Seemingly persnickety distinction, but it's going to end up being important. Okay, and then now let's compare these two functions, f and h. They have the same target. They have different domains. The f is defined for all students at Duke. H here is defined only for students in this room. Right? And okay, well, technically different domains, and so these are different functions. Okay. All right, a little bit of lingo. And this kind of has to get said. The thing on the right here, we call the target. The target is a set that all of the outputs land in. It can be any set that all of the outputs land in. It doesn't have to be anything else. It can have slack in it. You'll notice, for example, this student ID number function. I'm making the target z. Well, there's lots of integers that are not anyone's student ID number. No student on campus has a negative ID number or a 427-digit ID number, right? So this is way bigger than it needs to be. It's fine. The main reason we talk about a target is so we know what kinds of critters come out of this function. Is what sorts of are we talking about? The thing that comes out of the function, is it a matrix? Is it a color? Or is it a number, right? And so this is a way of saying, all right, look, this is an integer. Okay. So I want to distinguish that, though, then, with this thing called the image. The image is the set of actual outputs. What actually, literally comes out of this function. So let's see an example to see the distinction. So if we look at this function right here, perfectly good function, domain, real numbers, target, real numbers, rule of assignment, nice simple little formula here, that's a function. What actually comes out of this function? This is the squaring function. So when you square, I don't care which real numbers you square, when you square it, you never get a negative number. Right? And so the actual outputs, so what we call the image here, otherwise known as the range. I don't like that word. Otherwise known as the range, but the image, just the non-negative real numbers. Right? So notice the image and the target, not the same thing. Okay, so in some sense, you might say that the image is like the smallest possible target. Okay. All right. Okay. Let me say some things about this word range. I don't like using this word. Not that there's anything particularly wrong with the word, but it's just that the word gets used in different ways by different people. Tragically, in some books, the word range gets used to mean target. So it's really awkward, right, that we have these two things that are importantly different. The image and the target are importantly different things. We're going to see later on in a few minutes why it's important that they're different. And this word range, it gets used for both depending on who you're talking to. And so that's extremely confusing, and I find that basically unacceptable. And so because the confusion is now in kind of the culture, I just avoid this word whenever I can. So I'll always say image, unless I'm explaining why I don't like the word range. Okay. All right. A little bit more lingo. The output of a function is called the image. We say that y is the image of that particular input. Similar concept there. The input that gives rise to a given output. Naturally, we call that pre-image. It's the thing from before that gives you a particular image. So I think that's reasonable terminology anyway. Okay. Do notice that pre-image is not necessarily unique. You might have a bunch of inputs that give you the same output. Both 5 and negative 5, both square to the same output value. Right? So pre-images are not necessarily unique. Thus A and not the. Okay, now a little bit more language. And again, this is just this stuff has got to get said. Surjective, otherwise known as onto, and injective, unfortunately also otherwise known as one-to-one. And I feel like this terminology is also a little misleading. I don't want to go down that road, but you can say injective and surjective, or you can say one-to-one and onto. They mean the same thing. Surjective means that every point in the target has at least one pre-image. So let's go through this first function that I have over here. This point here has one pre-image. One is indeed at least one. This point here has two pre-images. 2 is at least one. Cool. This point here has one pre-image. That is also at least one. And so we have now successfully gone through the entire target. Every point in the target has indeed at least one pre-image. This function, therefore, is onto, aka surjective. Everybody good? Okay. All right. This function here is not. This function fails. Check out that point in the target. That's a point on the target, and it does not have at least one pre-image. It has 0 pre-images. Nothing hits that point. It's not the image of anything. So, failure, and this is not onto. Okay. All right, now let's talk about one-to-one, aka injective. What does that mean? This means every point in the target. Look at all the points in the target here. And we're going to have to make sure that every one of those points has no more than one pre-image. So at most one pre-image. So again, let's walk through and see what happens. This point here has one pre-image. 1 is at most 1. Cool. This point here has one pre-image. Again, fine. This point has 1, which is at most 1. And this point here has 0 pre-images, which indeed is at most 1. It is no more than 1. So victory. Every point in this target has at most 1 pre-image. And so one-to-one. Yes?
How come these definitions use the term target instead of image?
Because in some sense, if you look at the definition here of onto, right? If I say every point in the image, well, by definition of the image, every point in the image always has at least one pre-image. See what I'm saying? So, in some sense, don't think of, when you talk about functions as being either injective or surjective, I'm not describing the rule of assignment. I'm describing the trio, right? And so, in particular, surjective is a statement that depends on which target have you chosen. Does that make sense?
Yes.
Yeah. Cool. Okay. So, some functions are neither right? Because of this point right here, this function is not one-to-one. It's got two preimages, unacceptable. And because of this point right here, this is not on 2, because it has 0 preimages, unacceptable. Right? So this point here, this function here is neither one-to-one nor on 2. This function here is both. This function here, every point in the target has at least 1 and at most 1. And therefore exactly 1 preimage. And when every point in the target, let's see here, when every point in the target has exactly 1 preimage, that means you always get exactly 1 value there. You can think of these values as being the values of the inverse function. If I were going to define an inverse function, then for every point over here that I had been thinking of as the output values, I would need, as an inverse function, I would need to know for every one of these that there's exactly 1 previously known as input point that I can view as being f inverse. Right? So having exactly 1 preimage is exactly what you need to be able to talk about a function being invertible and to be able to define the inverse function. Yeah.
So if all the points in the target have the same preimage, that means
but that's not a thing. You can't do that. So it's an interesting question, and I hear where you're coming from. But you cannot have 2 points having the same preimage, because that would mean that this point over here, the value of the function, is 2 different things. And that's contradictory to the idea of a function. A function, for any given input, there is exactly 1 output. Now that output might have multiple coordinates or whatever, but it has to be a single thing. Is that satisfying?
Yeah.
Okay, good. Okay, so yeah, in order to be invertible, I need both 1-to-1 and on-to, and anything less just won't do. So let's see an example. This function right here, the squaring function, casually defined, is not invertible. 25 has 2 preimages. Unacceptable. -7 has no preimages. Unacceptable. Right? But I can restrict it. I can change the domain and the target a little bit. And this is what I like to call the invertible square function. Same formula, same rule of assignment, but different domain, different target. And here, everything's fine. If I consider only non-negative input values, and if I consider only non-negative values in the target, every non-negative in the value in the target does have exactly 1 preimage that is also non-negative. And so this is an invertible function, and its inverse, namely the square root, defined like this, is its inverse. Is everybody happy with that? Does everybody see how we have to? So we have to fiddle with the domain and the target to make it actually be invertible, so we can actually know what we're talking about, and this square root function is actually well defined. Okay. All right, and you've heard me say it before, and I'm going to say it again while we're here. Don't forget, then, this symbol, that square root symbol, means the positive square root. Always a positive number. Yeah. Or non-negative. Sorry, go ahead.
The G function has an input of like the negative numbers, and like we remove the positive numbers.
One more time. Say it again, please.
In the G function, if we remove the if we make the image just the negative numbers, is that okay, or is that?
You could do that. That would also be an invertible function, but that would be non-standard, and nobody does that. That would define a different thing, and this symbol is defined as the inverse of specifically that function. So yeah. But yeah, no, that's right. If we were a world of masochists, then we could totally do what you said. Yeah, right. Technically fine. Yeah. Okay, same deal with sine. And a lot of people think of sine as being just a formula, and you give me any angle, and out comes some real number. Right? But if you are kind of sloppy in that way and think of it as defined on any angle, which by the way is fine, and sometimes we do need to have it defined on any angle. But if you do let it be defined for any angle and think of the outputs as just being real numbers, not invertible. Right? You can make it invertible by restricting yourself to kind of, if you will, just this portion, namely just these angles, and restricting your allowed outputs to just these values, right? And notice for every green input, there is exactly one blue output. And for every blue output, there is exactly one green input. Right? Yes?
So, how do you pick a larger than angles? It would have not been invertible.
Correct.
Because there's multiple...
That's right. That's exactly right. If I had tried to say, let's, suppose I had said, I'm going to look at, like this, and I'm going to therefore be looking at, from negative pi over 2 to 3 pi over 2, if that's my domain, well, then for this y value, there's multiple different angles that give you the exact same the exact same value of the sine function, and so not invertible. Yep, exactly. Okay, so this particular restriction of the usual sine function is the conventional accepted, and you could make different choices, I suppose, but this is the conventionally accepted, what I like to call invertible sine function, and its inverse is what we call arc sine. And arc sine always takes a y value between negative 1 and 1 and returns an angle between negative pi over 2 and pi over 2. So you might think of it as going kind of that way on the unit circle. I like thinking about trig functions on the unit circle. I'll just, kind of point that out, that's kind of convenient here. Okay. All right. Okay, a little bit more language. I'm going to be quick about this. When you have a function like this where there's multiple input variables and multiple output variables, or at least possibly multiple of either of those, there are certain bits of language to describe this that kind of roll off the tongue a little bit more quickly. So whether there are multiple or just one output value, we talk about functions as being either real valued or vector valued. Real valued means there's only one number that comes out, namely the output is a single real number. If there's multiple numbers that come out, aka it's a vector that comes out, then it's a vector valued function. And then likewise, the variable of single variable and multivariable are talking about how many input variables there are, whether it's one input variable, single variable, or multiple input variables, multivariable. Okay. All right, you can read this for yourselves. Component functions are just the parts that make up a a vector valued function. Okay. So just to point out how common vector valued multivariable functions are, here is what I like to call the weather function. It is a multivariable function because it depends on multiple input variables. If you want to talk about the weather, you got to tell me where, how high above the ground, and when. Right? The weather depends on your altitude. The weather depends on your location. The weather depends on what time you're talking about. Right? The weather now is very different from the weather, tonight. Okay, so this is a multivariable function. And it is vector valued in the sense that there's a bunch of different numbers that you can use to describe the weather at, a particular time and place. You can talk about temperature, barometric pressure, wind speed, humidity, a bunch of other things you could add in there if you want to, depending on how much you like to talk about the weather. So, vector valued multivariable function. What I think is interesting about this is how, stereotypically trite, talking about the weather, right? It's the most, trivial of conversations, chit-chat, right? And yet, in fact, it's this sophisticated construction called a vector-valued multivariable function. Okay, so these vector-valued multivariable functions are all over the place, and that's what we're going to be studying in this course. Okay, how to understand them geometrically. So there's a lot to say here. The very first tool that I'm going to show you for visualizing multivariable functions is called the graph construction, and I'm going to start off by showing you the picture you've all seen before. This is an extremely common construction in a single variable calculus class, and the idea, of course, is that for every input value, there is a corresponding output value, and then you take the input value x, you make that the first coordinate, you take the output value y, you make that the second coordinate, and the pair with both the input and the output as coordinates of the same point defines a point on the graph. And then if you think about doing that for all of the different inputs, then you get a bunch of different points that defines the graph. Is that cool? Is everybody familiar? Does this look familiar to everybody, I hope? Okay. So the generalization of this is it just, it's really very much exactly the same thing. You take all the possible inputs, and keep in mind the inputs now are vectors, and so we have multiple input coordinates. And then you look at the corresponding outputs, again, also vectors, and so then there are multiple output coordinates. Again, you kind of smash them together and make a big point. And as you consider all possible input vectors, you're going to look then at all possible of these things, and altogether that's going to form this thing called the graph of that vector valued multivariable function. Okay, so it's just a generalization, same big idea, generalization of the single variable picture. So here's an example, function from R2 to R1. We have two input variables, so we're going to have two input coordinates, x and y, so you can think of our input space as kind of, sort of, if you will, loosely speaking, you can think of that as your xy plane down here, right? For any input value, you get one output value. We'll call that z. We'll put a z-axis over here as well. Smashing them together, inputs x and y, output z, all together we get points that look like this, x comma y comma z gives me a point up there in space. And if you consider doing that for all possible inputs, this entire plane of inputs, then you get an entire surface up there like that. That is your graph. Okay, so it's the same kind of thing, right? It's morally equivalent process. Just another example of this generalization. Just a little bit higher dimensional. Everybody good? Okay, here's another way to think about it, arguably a little quicker and easier. It depends on how you like to think about things. But when you have a function and you want to form the graph of that function, the graph is what you get when you set a new variable equal to the output value of the function. Yeah, so you got your function, whatever the output values are, set those equal to a new variable. So I had x and y as my inputs. I got this function called f. So I can talk about f of x comma y. Those output values we're going to choose to name them z. And in so doing, you write down this equation, and that equation defines your graph. And so surface. Okay. All right, here's another way to think about it. And this is really all the same stuff, just kind of said in a different way. Keep in mind, we're repeating some process for every point in the domain. Let me come back up here to the single variable first. Every point in the domain. For every value of x, we're going to go through this process, and effectively the function's going to tell us how far to push up from the x-axis. And if you do that for every point in the domain, you get the graph, which is a curve. Now, why is it a curve? You could argue that, well, I started with a one-dimensional domain, and every point in this one-dimensional domain is going to get pushed up, some by different amounts, depending on the function. But I've got this one-dimensional domain pushing all the points up by different amounts. Well, you expect it would give you a one-dimensional curve. Okay, so one-dimensional domain, the graph you would expect to be a curve. So likewise down here, with a two-dimensional domain, because there's two variables, right? Two-dimensional domain down here, every point of which gets pushed up, all by different amounts. Well, you would expect the result then to be also two-dimensional, and thus a surface. Does that seem reasonable? Everybody all right? Okay. Okay, so the dimensions are a bit of a thing to keep track of. We have here, for example, a function from R2 to R1, which makes the graph live in three-dimensional space. But because it is a two-dimensional domain, that's why we have a graph which is itself actually two-dimensional, namely a surface. Right? So a surface is a fundamentally two-dimensional thing that lives inside of a three-dimensional world. Does everybody see that distinction there? Okay. All right, so that's how you can. It's a convenient trick to be able to look at this and just keep in mind what role these numbers play, and they will tell you key information about the relevant dimensions involved in the graph. Okay, now let's try to do this same thing for this seemingly not that much worse function. We're just going to add one extra variable. Now only 3 input variables, and all of a sudden it's a crash and burn situation. 3 input variables are the first 3 coordinates of a point on the graph. 1 output variable is now the 4th coordinate of a point on our graph. And that means that my picture here lives inside of R4, and I can't draw 4-dimensional stuff. Right? And neither can you. That makes sense to everybody? So this is bad news. Right? What this means is that graphs, and before I finish that sentence, let me come back here and remind you, every picture you ever saw, practically, maybe 1 or 2 exceptions, overwhelming majority of the pictures that you saw in single variable calculus are of a type of construction that you just cannot use if you have 3 or more variables. So we're in trouble here. We're going to have a lot of functions with 3 input variables, and we're going to need to understand them. And it's going to be very useful to have pictures to describe them, and I cannot use their graphs. It just doesn't work. Is that cool? Yes?
How would you build, an intuition into understanding?
That's right. That's a great question. The natural next question. So we have various different tools, and I'm going to be going through them for kind of the rest of this lecture, and I think we'll finish it by this lecture. Yeah, exactly. Okay. All right. So we're going to basically build other constructions. So the following is going to be a little bit of an adaptation that y'all are going to have to get used to. You may have, as a result of single variable calculus, kind of gotten accustomed to the idea of conflating a function with, the graph of the function. Because whenever you have a function, you can always make the graph. The graph gives you a tremendous amount of information. We're super comfortable with it. And so it's not like there's any other pictures that we've ever drawn of single variable functions. So it's tempting to just think of these as being morally equivalent. And very importantly, they're not going to be in this course. So you're going to have to kind of let go of this idea and realize that this graph construction is just one of several different constructions that we're going to have that allow us to kind of form some sort of a picture with which we will get some sort of intuition for understanding functions. So heads up, again, this is an adaptation. You're going to have to sort of disconnect these ideas in your mind. A graph of a function is not the same as the function itself. It's just one of many tools. Several others that are going to be very important that we're going to start in on now. Okay, so here's my next one. I call this the literal picture of a function. The kinds of pictures I'm about to draw here are all over lots of textbooks, and I've never heard a name given to them. So I call this the literal picture of a function. And the reason is because if you have a function from, let's say, R3 to R1, and keep in mind what a function does. A function takes points out of the domain, puts them in to the target. Right? Well, check out my picture here. There's a picture of the domain, literally. And here is a picture of the target, literally. And now notice that my arrow here is suggesting the process of taking points in the domain and literally dropping them down into the target. So this is about as just a bluntly, purely representative picture of what the function is actually doing as we can draw. That's what a function does. Does that make sense? Any questions about that? Now I want to recognize this is a very disappointing construction. You look at this picture and you think, okay, but where's the shape? How am I going to use the geometric features of the shape, like slope, for example? We're accustomed to seeing a slope of a curve and being able to make an interpretation of that. Oh yeah, slope tells me about the derivative, right? So geometry, the slope of the curve, we're accustomed to telling us critical information about the algebra, namely the function itself. I see no shape here, so there's no features of the shape that I can look at because there is no shape. How could this possibly be useful? So I'm going to say two things about that. For one thing, for a function from R3 to R1, it's not like I had any alternatives. Right? So the graph construction is purely inaccessible. I cannot draw this picture at all. And in a kind of a beggars and choosers kind of a situation, well, it is at least a picture. It's something better than nothing. All right? Does that make sense? Here's the other thing. There is more to do with pictures than just representing the shape of the function. Sometimes a picture will help us represent a story or a question. So, for example, here's a reasonable question. Let's suppose that I am at that point A. I got some function that's defined everywhere in space. Maybe the function is representing temperature. I think we talked about that one at the start of class. So here's the space where I'm, flying around, and at every point in space there is a corresponding temperature. Okay, well if I'm at the point A, and if I'm moving with velocity like that, that's my velocity v, the output value for that point will be some number, and as I move, that output will move with some velocity also. Right? So a reasonable question to ask is, if I'm at this point, where I know what the temperature is, at this point, if I'm moving with some velocity in the domain, that'll cause this point to be moving with some velocity in the target. What's the relationship between this input velocity and that output velocity? Very reasonable question to ask. In fact, this is going to be one of the big questions we'll ask about multivariable differentiation. And much to say, that'll come in a little while. We got a lot to develop before we can really answer that question. The point here, though, is that this picture gives me this kind of a picture, this construction gives me a way to draw a picture of what the question is asking. It doesn't answer my question for me, but it allows me to represent the question that I'm trying to get my hands on. I can see the point where I'm at, I can see the velocity that represents my motion, and I can see what I'm interested in trying to figure out, namely how fast is this image moving. So it's useful even if it doesn't show the whole function in some sense. All right? All right. Okay, here's the next kind of a picture called level sets. So level sets are pre-images. Keep in mind what a pre-image is. A pre-image is an input that gives rise to a given output. Okay, so the way we define this, by contrast with graphs, let me come back up here to the graph picture. Okay. So a graph is where you take a function, whatever function you want to form the graph of. The graph says set that function equal to a new variable. Okay, by contrast, a level set says we're going to take whatever function we want to form the graph of, and we're going to set it equal to a constant. That's the definition of a level set. Very different from setting the function equal to a variable. We're instead going to set the function equal to a constant. And so again, this means that we're talking about a pre-image. The level set itself, once you've said I want to set the output equal to some value b, the level set itself is the collection of all of the corresponding input values. What are all of the input values that give you that corresponding output value? Let's see an example. Get our hands dirty. Here's a function. There you go, perfectly good function. Notice that I am drawing this in the kind of the literal way, right, where I have the domain over here and the target over there, right? So, with that in mind, I'm going to now set some output values and find the corresponding input values. Let's set our output equal to 1. What happens when I set f equal to 1? Well, f is x squared plus y squared. Setting it equal to 1 gives me this equation here, x squared plus y squared equals 1, and that's an easy equation to understand. That's just a circle. Right, so what we have then all together, we have that all of these points all land on this same output value, 1. So, given an output, we look at all of the corresponding inputs that land on it. And thus the idea that this is a pre-image, because instead of looking at inputs and seeing what the outputs are, we're looking at an output and kind of reverse engineering to find what all of the corresponding inputs are. How are we doing on that? Does that make sense? Okay. All right. And of course we can do this for multiple different values. Let's do it for the value 2. Set the value of the function equal to 2. That gives me a circle where the radius is the square root of 2, as it turns out. So a different curve. And you can repeat this as many times as you want. You can take as many different output values as you want, and you keep getting different curves. Now, of course, here we happen to get concentric circles because that's the nature of this function. But the more outputs you look at, the more curves you get, and that tells you in some sense, well, I'll say this, at least it gives you a picture that you can look at and something that you can possibly make some interpretations out of. Now, how do we make interpretations out of it? I have a favorite sort of first example on this, and that is topographical maps. And I don't know if if you've done any hiking, you've probably seen this before. They have these on Google Maps also. If you zoom in at just the right level, you can't zoom in too far or too little. It has to be just the right level. And you hit the, what do they call it? There's a name, on all the options, the layers that you can get on Google Maps. I want to say, maybe it's called Contour? Anyway, there's an option. If you click through, you'll find it. So what it is a topographical map. So a topographical map says it shows a bunch of curves like this called contour lines, each of which represents a constant value. Let's say maybe this is 400. A constant value of the altitude function. right? Given a location on the map, you can ask what is the altitude of the surface of the Earth at that point on the map. Contour line is all the points that have a specific value, for example, 400. Okay, so when you see a bunch of contour lines, though, you start to get some idea of what the shape is actually that you're looking at. So here's a bunch of contour lines, and each one of these contour lines represents a different altitude. Each, let's say, between contiguous contour lines, maybe that's 100 feet, right? And so, don't you kind of get a vibe here that the higher up we go, sort of the smaller it is, and doesn't that kind of look like the top of a mountain? Kind of, sort of, right? So we've gotten some idea of what altitude is looking like. No graph in sight. We're not looking at a graph, right? But we see some information about what this looks like based on these lines. And I guess I have to draw the line right here. Seems we're out of time. We'll pick up here next time. And see y'all later. Hope y'all have a great weekend. Don't forget, homework's due tonight, I think, right? Make sure to, don't forget on that. See y'all later.